Welcome to Chapter 3, which is all about numerically summarizing data. We spent last chapter talking about how we can display data information, but now let's get some measures, some numbers that will summarize our data. The first three measures we're going to look at is measures of central tendency. These will be ones that you're sort of familiar with. We have the arithmetic mean for a population or sample, which is the average of the data set. You can see in the formulas that the population average or population mean is represented by the Greek letter mu, mu, and it is the sum of all data entries divided by the population size. Now, being that we don't typically have an entire population represented in our data, we also have a formula for sample mean, which is represented by x bar. That's how you would pronounce this, x bar, which again is just the sum of all of the values divided by the number of values in our sample. So you add them all up, divide by the number you are adding up. That has always been the average. It's always been the mean. Then we're going to introduce the median. The median is the value that lies in the middle of the data when arranged in number order. So we're going to be sorting our data from smallest to largest so we can find whatever's in the middle. Hopefully you remember also that if two numbers lie in the middle, you will average those two numbers to find the median of those two median numbers. The mode of a data is the most frequent observation of the variable that occurs in the data set. A set of data can have no mode, one mode, two modes, or be multimodal. But really, once we get past bimodal, we would really say there is no mode because having a multimodal set of data is not really that helpful. So really, your answers are going to be no mode, one mode, or two modes for particular data sets, although multimodal is a thing. Now, as we look at these measures of central tendency, it's very It's very important to understand the idea of resistance. So when we're talking about the resistance of a measure, we are talking about how resistant it is from extreme observations. Meaning, if we were to throw in a really, really large observation compared to everything else, would that numerical summary, whatever we're looking at, change substantially because of that extremely large or extremely small value? If it does change, it is called a non-resistant numerical summary. In regards to mean, median, and mode doesn't really work in this instance, but if we're looking at the difference between mean and median, if you have symmetric data, mean and median should be exactly the same. But once we have data that's skewed either to the left or to the right, notice that the mean and median are no longer the same, and that the mean has shifted off toward the tail of the data, which means that mean is not resistant, but median is pretty resistant to these extreme observations. And that's very important to think about when you're telling me about data, because it might be better to report your central tendency with the mean or with the median, depending on what kind of data you have. If you have symmetric, you're going to want to report the mean or the average. But if you have skewed data, it's going to be better to tell me about the median because it is actually closer to the middle of the data itself. Now, this would have been more exciting if we were in class, but our example today that we're going to take as a sample from you guys as a sample is how many letters are in your full first and last name. Now, obviously, I'm not there. So we're going to have to just use all of the same data. So I made up a class and I made up a bunch of names and I counted the number of letters in first and last names for this class that I made up. So let's go ahead and write these down. This is the data we're going to be using to explore these measures of central tendency. Now, you're also going to want to have your Excel open. So as you're watching this video, I'm going to go through Excel skills and I might go a little fast, but isn't it nice? You can stop and pause this video when you need it. Great. First question, does this data represent a sample or a population? This represents a sample because if we were talking about all of my students' class, like all of Miss Quigley's classes, y'all are one of my class is. If we're talking about all of Mesquite High School, you guys are one class out of all of Mesquite High School 1A or 2A classes. So this is a sample of a larger population. So when we're finding the mean, we're going to use X bar as our value. So we could go to a calculator or Excel and we can add up all of these numbers, divided by the number we have, which is 27, we'd get 13. But let's see in Excel what that would look like and practice our Excel skills. So here's all of my data. Again, you're going to want to have this typed in. So go ahead and do that. Pause the video and do that now. But if I'm working with this information, what I'm going to do is I'm going to have all of my data, and I'm going to find the average. Now, I know based on what I'm going to have you do later that I actually want the average to be listed in A1. So we are going to right click and we're going to insert a column to the left, and look, it scoots all the data over. In fact, I'm going to have you insert another one, and I'm going to have you insert a row above this one because I want this data starting in C2. Now we are going to find the average or the mean, X bar, if you will, and telling Excel to do the average of these cells. So from what is now C2 to C28. And I'm going to round this to, I'm not going to bother doing the increase, decrease decimals, but you can. So our mean is 13.0. That makes sense. We find the median. Median is best done if we have data sorted. So what we're going to do is we're going to take our data. We're going to, again, right click. And we're going to sort from smallest to largest. I'm just going to sort that one column. And I can see that out of my 27 things listed, I'm really looking for the 14th item so that there are 13 things above it. That's 13. And 13 things below it, which means that my median is 12. That was the middle number of my data. Now notice these are not the same, so it's going to be very interesting. It's not too far off, but it's not the same. If we go to find the mode, you'll notice that I have 6 entries that say 11 and 6 entries that say 12. So we have a bimodal set of data with 2 modes of 11 and 12. Now, the next part here asks you to draw a histogram and think about the shape of the histogram. Hopefully you remember how to do this. I'm not going to stop and think about it again because we've already talked about in class how to make these histograms, or really it's a column, a column chart. But you can fill that in on your own. The next question asks, is the mean or median larger for this data and why? The mean is larger here, obviously 13 is bigger than 12, because it is more affected by this large observation of 20 than the median is. We had one student who had a lot of letters in their name, and that threw off our center because we had this very large observation. But notice that the mean really does show me where the center of my data is. There is more data here than there are out here in 13. This is going to be a better telling of the center of the data, which is, again, what kind of part G is talking about. We would want to report the median here because of the skewedness of this data. It describes the true center of the data better than the mean does because this data is skewed to the right. Now, we don't just need to use central tendency to describe our data. We can also use measures of dispersion. Now, you might not have ever used this word before, but this is really just telling me how spread out the data is. How spread out are the values that we have. The first and probably easiest measure of dispersion that you're used to is called the range, which is taking the largest data value minus the smallest data value. Of course, a lot of this math is easy and in our head, but we can always do this in Excel. So our largest value is 20 and our smallest value is 9. So we can tell Excel to do our largest minus our smallest, and it would tell me 11. I could have done that in my head, but there we have the range. And voila, that was the first question. Got ahead of myself a little bit. Standard deviation, I'm going to make this bigger to talk about standard deviation. Standard deviation is a very normal, that's the wrong word to use in statistics. It's a very typical way for us to talk about the spread of the data. And it's talking about how spread out from the mean are we. That's what standard deviation reports. Now, the formula for standard deviation for a population and for a sample looks really complicated, and saying it is very complicated, but doing it is not all that complicated. Population standard deviation is represented by the Greek letter sigma, and we would pronounce this as sigma is the square root of the sum of the squares of all data points minus the mean divided by the population size. So we're going to find the mean. We're going to subtract the mean from each and every observation we have. We're going to square those numbers. We're going to add up the squared numbers. We're going to divide the sum by the total population and then take the square root to get sigma. A sample works pretty much the same way, except that notice mu has turned into x bar because we're going to use the sample mean instead of population mean. And notice that in the bottom, we now have n minus 1. This is important. I would highlight that. N minus 1 is called the degrees of freedom. We need degrees of freedom when we're doing standard deviation of a sample because we know that a sample might not truly represent the population, and this formula allows a little bit of leeway when we do n minus 1 in the denominator for that mistake of not exactly representing the population. So notice again, population is capital N for population size. For sample, we're doing sample size minus 1. So if we have, for us, 27 numbers in our sample, we will be dividing by 26. The last measure of dispersion is variance. It is just another value we can give to talk about how spread out the data is. It is the square of the standard deviation. In fact, population variance is sigma squared. That's how you would report it. So you just square this bad boy. And sample variance, is the square of sample standard deviation. So you just undo the square root, which does mean in the method I'm going to teach you to calculate population standard deviation and sample standard deviation, you will already be finding variance. You just have to back up a step. Notice that standard deviation is not resistant. So if we have extreme values, which we do in our data, and we're just going to politely ignore that for today, it's not the best method of talking about the spread of the data because of these extreme observations. And standard deviation using the mean is not resistant. So standard deviation is not resistant. Okay, so what we're going to do is we're going to use the sample from earlier. We're going to find these measures of dispersion. Now we are going to pretend that the data we have is both a population and a sample, so you can see both formulas. I've started this one already for you. We calculated the mean earlier. We are going to end up calculating all of the rest of that. So let's go back to Excel so I can show you the sort of thing we're setting up, which, by the way, if I go too fast, 1, slow down this video, and 2, you'll notice at the bottom, I have an example Excel sheet that is set up for how I would encourage you to find standard deviation. You don't have to give me titles, but it's very helpful because we're going to do some complicated things. Notice that all of my formulas here don't have equal signs in front of them. You should put equal signs in front of them. But here we go. Let's find the standard deviation for this data. I'm going to make this side larger now. Okay, so we have all of our data values. We have our mean. The first thing we're going to do is we're going to subtract. So I'm just going to call that title subtract. So I'm going to take this cell and I'm going to tell it, I would like for you to take the data entry I have in C2, and I would like for you to subtract the mean. And it's going to do that. If I were to copy this formula down, don't do this, but watch. If I copied this formula down, it says C2 minus B1, that's good. But then it does C2 minus B3, and I have the range there. That's not what I wanted. And in this one is C4 minus B3, which there's nothing even in B3. So what we need to do is we need to make B1 sticky because we want all of these values to subtract from the exact same cell. You'll notice I guess I should be showing this whole time, in here that I have these dollar signs around B1, which is where my mean is. When we are doing a formula where we want to reference the same exact cell every single time we copy this formula, you put a dollar sign in front of the row and a dollar sign in front of the comma to make them sticky. Now, that's a misquiggly term to make it sticky. It's called referencing or locked references if you were to Google stuff for this, but I think it's fun to call it sticky. But so now that it's sticky, notice if I copy this formula down, the C3 is changing in the formula bar, C4, C5, but B1 has not changed because that's the only place I have my mean. So I'm going to copy that down. Okay, cool. So I've subtracted them. Now I need to find the square. So I'm going to say equals this cell, shift 6 squared. Because I want to square whatever is in D2. Now I want to do this for all the values. So I'm going to copy that formula all the way down. Nothing is sticky because I don't want it to change. So we have subtracted the square. If we look back at the formula, after we subtract the square, we're going to add it all up. That's what this summation symbol means. So I come down here just because I like to show my work and I like to know what I'm doing. This is the sum. So I'm going to do equals the sum, open parentheses, go back up. Let's gather all of this stuff, close parentheses. There's the sum of the squares of the differences. And then I'm going to divide. Assuming this is a population this first time, I'm going to take this cell and I'm going to divide it by the number in my population, which is 27. Then I'm going to square root. Now the shortcut for square rooting something is like on Desmos, SQRT, that's how Desmos got its language. That is computer language for square root. And we're just square rooting the number that has our division. And voila, we have our population standard deviation. Now, if you'll notice, I kind of broke this down bit by bit. So we have the sum, we have divided by, and then we have sigma, our population standard deviation. Now, these formulas only get different in the very last step when we get to degrees of freedom, because we are no longer dividing by population size for sample standard deviation. We are dividing by the degrees of freedom. So what I'm going to do instead is I'm going to say, okay, I'm going to divide by degrees of freedom. So I take the sum and I divide by my population minus 1, or sample size minus 1. Again, we're just assuming at this point we are working with a sample. Then we can just take the square root of that value, and voila, I have the sample standard deviation. I guess I should call this the square root. So again, to summarize, and it's all here in this picture, I did the average, the mean. I have all of my data. I have the subtraction step, observation minus x bar or mu. I square all of those terms. Then I add up all of the squared terms. Then I divide that sum by either population size for population or by degrees of freedom, which is sample size minus 1. Then I take the square root of both of those division problems to find standard deviation either for the population or for the sample. But here's what's nice, because there's an extra question here that says find the variance. Notice we already saw these numbers once. Before you square root, these numbers right here tell you the variance for either the population or variance for the sample. What does standard deviation actually tell us? Thank you so much for asking. Standard deviation, since it represents the typical deviation from the mean, it basically allows us to judge whether a particular observation is far away from the mean data set. For example, if I were to ask you, is 5 far away from 0? So I have 5 and 0 circled here. 5 is not that far away from 0 unless standardly the standard deviation away from 0 is 2, meaning if my mean is 0 and my standard deviation is 4, this is 1 standard deviation away from 0. This is 2 standard deviations away from 0. 5 is within the 1 to 2 standard deviations away from 0, so it's not that far away. But if my standard deviation was 2, here's 1 standard deviation. Here's my second standard deviation. The observation of 5 is further away from 0 since my standard deviation is smaller. So a good rule of thumb is to consider an observation far away if it is 2 or more standard deviations above or below the mean. Meaning, if it is more than 2 away and above it, or more than 2 away and below it, we would call that far away from the mean of data. In statistics, we are going to call that observation unusual. Now, all of this leads to what's called the empirical rule, and it is really helpful for bell-shaped data. You'll see this large picture, I think I have to zoom out a little bit, that explains the empirical rule. Notice in the middle, at the very height of this bell-shaped symmetric data is mu, our mean. And then we have standard deviations above and standard deviations below the mean. So this is 3 standard deviations below, 2 standard deviations below, 1 below, 1 above, 2 above, 3 above. Statisticians have done enough research to understand that between 1 below and 1 above standard deviations from the mean, 68% of our data lies within that standard deviation, meaning 34% of it below the mean and 34% of it above the mean. We've also done enough research as statisticians to know that 2 standard deviations away contains 95% of our data. 34 and 13.5 on this side, 34 and 13.5 on this side. We also know that 3 standard deviations away from the mean, above and below it, contains 99.7% of our data, meaning that there is only 0.15% of data that is beyond 3 standard deviations away from the mean. This again is for bell-shaped data, which allows us then to draw some conclusions. Now we are going to pretend that our data was bell-shaped. It was not, it was skewed. But for class's sake, we're going to apply the empirical rule for bell-shaped data to our data we got so we could maybe answer some questions. Again, our data is not bell-shaped, but we're going to just ignore that fact politely. So what I like to do in Excel, and I did do this in Excel, and I'll show you a couple examples of this, is I set up something kind of like this, where I put in column 4, which would be column D, I repeat my mean. In the 3 columns before it, I will take the mean and subtract one of my standard deviations and get 10.6. The next column over, I will subtract 2 times the standard deviations, which, by the way, Shift 8 is multiplying in Excel. And 3 standard deviations, 1 above, 2 above, 3 above, to get the values of my empirical rule so that I can answer questions that follow. So let me show you how I calculated this in Excel, basically using Excel as a calculator. So what I did here is I have my mean just copied from the table above. So it just says equal to B1. Scroll up so you can see that. Equal to B1. And then to find one standard deviation above, this is a sample, so we use the sample standard deviation. I just did this cell plus this cell. To do 2 above, I did the mean plus 2 times my sample standard deviation, and on for 3, 1 minus, 2 minus, 3 minus. So I have my values for my table that represent the empirical rule for this data, which allows me to answer the following questions. The first question says, about 68% of students in this class have between 11 and 15 letters in their name, because it needs to be more than this, and since we're using whole numbers, we round that to 11, and less than this. We would round that up to 16, so it would be less than that. 95% of my data, which is 2 standard deviations away, 9 and 17. 99.7% of students, that is my 3rd standard deviation away, so I have to have between 6 and 20 letters in their name. So a question that would follow up, again, you see this word unusual. Would it be unusual for a student to have 8 letters in their first and last name? Yes, because that falls outside of my 2 standard deviations from the mean. Now, it's still allowed. Miss Quigley has a friend named Amy King. That's only 7 letters in her name. It's unusual for somebody to have that few letters in their name, but it's not wrong. Now, this video is getting a little long, and I know you're getting lost in the sauce when it comes to Excel. So this last one is for you to practice. I am going to linger on this page for hopefully you to stop the video, take both of these data sets, and do the different things we talked about today with your data sets. I'm going to scroll down to have a filled in version of this showing at the end of this video without any explanation, but I really want you to stop and pause and make sure you and the people around you can do the Excel skills for this lesson. So pause the video now. Hopefully you pause the video because I'm going to scroll down to see the answers. I'm going to scroll again. Pause if you weren't ready. Hopefully you got a little bit of the skills for central tendency and spread. We're going to talk about these things again next time when we look at grouped data for central tendency and dispersion.